Dr. Ramunas Levinas.
Is
He will
everything
talk
fine?
about our prospects of using molybdenum sulfide for photoelectrochemical water splitting. So please, welcome.
Okay, thank you. So the title of my presentation is, yes, molybdenum sulfide containing coatings for photo and photoelectrochemical water splitting applications. So the reason why we work with catalysis is because of renewable energy goals. So the European Union did decide on goals that by 2020, almost 20% of the EU's consumed energy should come from renewable sources. And obviously 2020 passed and the goals were met with satisfactory results, enough that a new renewable energy directive would set an even larger target to be reached within a decade. And so hydrogen, it's not an energy source, but it is a good energy storage medium because of its very high energy density. However, green hydrogen, that is to say hydrogen that could be produced without the emission of pollutants and greenhouse gases, is not yet financially viable for widespread use. And it is currently thought that, well, water splitting could be a simple way. It is a simple way to produce green hydrogen, but to make it economical, the amount of energy that is required to split water electrochemically should be reduced. And for that reason, we use certain materials called catalysts in a process that is called heterogeneous electrocatalysis or photoelectrochemical catalysis. So the reason we use molybdenum sulfide is that it is a fairly versatile and functional material. It is a semiconductor. It can have, can have various morphologies, which depend on the way in which the material was synthesized, and there are many ways to synthesize this material. In this study, it is mostly electrochemical, which I will talk about later. The material has an interesting structure, and in the structure, it has active sites, which are typically sulfur vacancies. And these vacancies have a favorable energy specifically to absorb hydrogen. And that is why this material is an excellent electrocatalyst for hydrogen pollution, but it can be used for other heterogeneous electrocatalysis processes. And again, the reason it is useful in water splitting is because, as shown is this volcano plot, which plots the free Gibbs hydrogen absorption energy against the exchange current density of the catalyst. Molybdenum sulfide is near the top of the plot. These are specifically edge sites, but other sites can have different energies. The material is often, its mechanism is similar to that of platinum, and it is highly efficient. So in this study, we synthesize molybdenum sulfide electrochemically. That means that the first part is cathodic deposition, electrodeposition from an aqueous precursor solution. The precursor is tetrathiol molybdate. And the deposition can occur through this reaction. We use various substrates. So we use a simple copper wire, which we consider a 2D surface. And of this surface, we know the geometrical surface area, which is 1 square centimeter. Also, we use the femtosecond laser ablated copper foil surface. The surface is represented by this profilogram. And from profilometry, we know that while the projected surface area is 0.25 square millimeters, the developed surface area, that is to say the surface area that is measured by the falling light, the incidence of light, is about 40 times higher. So this is a relatively very high surface area material. In addition, we tried the position of on electrodes with what is essentially an uncertain surface area. So for example, these metallic copper foams. There's just no way to measure with simple measurements the surface area of this material. And the reason I'm talking about surface area is because in heterogeneous electrocatalysis, it is very important to distinguish between the geometrical, the electrochemically active, and even the electrocatalytically active surface area. As shown in this graph, which is a citation from a paper, the geometric surface area can simply be thought of as the surface of the material. The electrochemically active surface area is the area on which charge can accumulate, and the electrocatalytically active surface area in this graph is represented by active sites. So it's in heterogeneous catalysis, the process does occur on active sites typically, so the electrocatalytically active surface area can be very different from the geometrical surface area and even the electrochemically active surface area. So these materials had been deposited, molybdenum sulfide had been deposited on various surfaces. On copper wire, the SEM images show that the morphology is fairly flat and featureless. On the femtosecond laser ablated surface, we notice the deposition of sort of micro or even nanocrystalline crystallites. And on a copper foam, we don't really investigate the nanomorphology, but we see that the overall coverage of the foam does occur across, as far as can be told from ICM images, across the entire foam. And the reason for using these different substrates is also different catalyst loadings, which are represented here by charge passed through the system, can be obtained. Because if too much material is deposited on a flat surface, that is to say, too much charge is passed through during electrodeposition on a flat surface, this film tends to delaminate, crack and delaminate from the surface. Whereas on rougher, more evolved surfaces, larger amounts of molybdenum sulfide can be deposited, and for various reasons, the film is not compact and thin, but it is perhaps more microstructured, and therefore it adheres better to the substrate, which matters a lot for the stability of the film. So we measure hydrogen evolution reaction electrocatalytic activity by drawing linear sweep altimetry curves in an acidic media, 0.5 molar sulfuric acid. Again, the three different substrates are compared here. So on a wire, we change catalyst loading, or the amount of material deposited, by simply increasing the time of deposition. And it is clear that the longer the time of the deposition, then the catalyst is more active. That is to say, it reaches higher current densities at lower overpotentials. And the most catalytically active film is the one that had been deposited for almost 2 hours. Now, on a femtosecond laser ablated surface, we only examined a single charge, which is 5 coulombs, as the amount of material deposited. Even then, we can see that the material reaches, it is fairly electrocatalytically active, and even more so than a comparable just film that had been deposited on a non-laser ablated surface. And on copper foams, again, the same trend of charge is being continued. So then more charge has been passed and more material deposited on the copper foam electrodes. And again, we see that these electrodes reach even lower, even also high current densities at lower overpotentials. So the overall conclusion is not surprising that the hydrogen evolution reaction related activity is tied to the amount of catalyst that is deposited. Yes. Now, because the surface area is difficult or impossible to measure in certain films, we use electrochemical impedance spectroscopy. And electrochemical impedance spectroscopy is especially useful to characterize surfaces, that is to say, reactions that occur on the surface and heterogeneous electrocatalysts. In this method, effectively what we do is apply a certain perturbation on the applied potential in potentiostatic electrochemical impedance spectroscopy. So the potential is modulated by a certain frequency. There are different frequency points. And in the system, the response is a current density, a current that is also follows the modulated potential. There's a certain phase shift between them. So we carry out, to characterize fully a single electrode in hydrogen evolution reaction, electrocatalysis, we obtain We obtain an electrochemical impedance spectra at different overpotentials. So this is a simple polarization curve for the sample, and shown here are the overpotentials at which the impedance spectra are obtained. And it should be noted here the steepness of the curve. And the spectra that are the resulting spectra obtained on a foam electrode, on a molybdenum sulfide film deposited on a foam electrode, are shown precisely here. The spectra are characterized by two important features: a high frequency response here, which is very small, and it is similar, relatively similar for when obtained at all overpotentials. And the low frequency response, which is the larger semicircle. And it can be seen that this semicircle its magnitude decreases significantly with applied overpotential. And shown below are the so-called Bode coordinates, which are slightly different units. On the y-axis here is shown the phase angle and the impedance magnitude. So the impedance magnitude is proportional to the conductivity of the system, and it is not surprising that as overpotential is increased, as more hydrogen evolution occurs, as can be seen from the polarization curve, the impedance magnitude decreases. And regarding phase angle, the response is more in phase with the perturbation. And the results are interpreted by equivalent circuit fitting. So in this case, the present circuit was used, and the circuit has two important components apart from the electrolyte resistance. So the high frequency component, which is comprised from double layer capacitance and charge transfer capacitance, and more importantly, the low frequency component, which is comprised from absorption capacitance and absorption resistance. Precisely these two parameters limit the current electrochemical reaction. But plotting these parameters here, as shown, the absorption resistance measured at an overpotential 0.1 volts. But for molybdenum sulfide films that had been deposited on various substrates for a certain amount of charge, we notice a very clear exponential extinction trend. So the circles here are molybdenum sulfide films that had been deposited on a wire electrode, and process X's are films that had been deposited in foam. We notice a very clear exponential extinction curve of the parameter absorption resistance against deposition charge. And interestingly, well, perhaps not surprisingly, we also find that the femtosecond copper molybdenum sulfide film also falls, which was deposited for 5 coulombs, also falls fairly within this range. So regardless of the geometry or the morphology of the electrode, we find that ultimately the overall activity, the charge transfer absorption, resistance is mostly related to the deposition charge. And this allows us to compare different electrodes without normalizing surface area into milliamps per square centimeter or so on. We also measured local electrochemical activity, which was done by scanning electrochemical microscopy. Very briefly, it is a method in which a probe of a very small diameter, in this case 10 micrometers, is lowered toward the surface of a sample, which in our case was the molybdenum sulfide film on a femtosecond copper laser ablated surface. A substrate generation tip collection mode is used, which means that on the substrate, hydrogen evolution occurs and hydrogen gas evolves, but preferably not in bubbles, but small enough amount to dissolve in the solution. And the tip is polarized to oxidize this gas to obtain electrons. And these electrons are the signal that the potentiostat obtains. And in this way, the probe is moved across the surface. We obtain 2D heat maps. And although these maps are not particularly expressive, the 2D slices very clearly show that the tip does register the surface morphology. This dotted line is shown from a profilogram. of identical dimensions in micrometers. And the hydrogen evolution reaction activity does follow this profilogram. So in this way, we can measure differences in local hydrogen evolution reaction electrocatalytic activity. Now, regarding the second part of my presentation, we synthesized tungsten oxide and molybdenum sulfide photoanodes. These composites were synthesized by anodization. So by anodizing tungsten in the following electrolyte, we obtain tungsten oxide. However, if molybdenum tetrathiomolybdate, this is only an ion, is added, it can deposit anodically, the process also called disproportionation, into molybdenum trisulfide with some elemental sulfur also depositing. The result is essentially a composite of tungsten oxide mostly, with molybdenum sulfide dispersed, well, in some way throughout the material, as shown by these EDX maps, both cross-sectional and top-down. The surface morphology of these samples is fairly unique because it is not nanoporous, or it is not very ordered, because the anodization is carried out in such a way that some plasma discharge occurs. And as the plasma discharge occurs, this creates certain pores that can reach towards the base metal, the tungsten, and sometimes they do, sometimes they don't. What is important to us is that we notice that when the material has been synthesized by anodization for 2 minutes, fairly thin fairly thin film is formed with small nanopores. However, when the process takes 30 minutes, then much more molybdenum sulfide is deposited, which has also been shown by EDX. And these films have been characterized for their photoelectrochemical properties. The characterization was performed in an acidic sodium sulfate solution with a 365 nanometer near UV light source. The initial experiments performed were chopped UV linear photometry under illumination by 50 milliwatts per square centimeter. And as the potential is scanned toward the anodic direction, the UV light is also incrementally switched on and off. And this gives a good idea of how both the background current and the photocurrent depend on the applied potential. The overall result we see from these graphs is that comparing the base tungsten oxide with the composite generates far larger photocurrents, whereas the so-called dark current is similar. The UV on-off pulses at a chosen potentiostatic conditions, in this case 1.2 volts, were also performed. And these experiments should show whether the material has surface recombination. If there were surface recombination, the initial photocurrent would have a jump, which would then settle at a constant value after some time. There is no initial jump in this case, which means that there is little to no surface recombination. And when comparing films that had been synthesized by anodization for different times, that is 2, 5, and 30 minutes, we noticed that the most effective film, which gives an incident photon conversion efficiency of 3.1%, is obtained as the composite film that had been synthesized for 5 minutes. However, another result that we notice is that the relative difference between the tungsten oxide and the composite is much larger when the film had been synthesized after anodization for 30 minutes. So the composite does have more effect, not on thin, not on thin, but on thick films. Very briefly, I would like to talk instead of intensity modulated photocurrent spectroscopy, about photoelectrochemical impedance spectroscopy, which was more useful in characterizing these particular samples. So this is a very small modification of simple electrochemical impedance spectroscopy because the sample is illuminated. So if the sample is illuminated, then according to the Gartner equation, the photocurrent is decided by many variables, among which W, marked here W, is the width of the space charge layer. And the width of the space charge layer is proportional to the applied potential. So assuming everything else is held constant, that means the photocurrent will depend on the width of the space charge layer as we modulate the potential and keep the sample illuminated. What we obtain then is so-called photoelectrochemical impedance spectra, which differ from electrochemical impedance spectra because, as can be seen here from the two curves, the black dark curve, which can be imagined as the curve that would be obtained by polarizing the sample without illuminating it, and the red curve, which is a photocurrent potential dependence. The impedance that would be obtained for these, the dark curve, the magnitudes, the profile of the spectra and the magnitudes are fairly similar. However, for the photo EIS spectra, we know that as the photocurrent increases, there is a larger difference in the magnitudes of the spectra if one were to compare these two. And the photoelectrochemical impedance actually increases rather than decreases, which would be expected for EIS. So again, we approach these spectra by modeling them with an equivalent circuit. The equivalent circuit is shown here. And it has, again, two components, a high-frequency component, double layer and charge transfer capacitance and resistance. But more important are the space charge layer capacitance and resistance. And the space charge layer in the theory of, well, photoelectrochemically performing materials, the space charge layer is the near surface layer where the generation of photoexcited charge carriers that takes place. That is to say, it is the region where light penetrates into and electron and hole pairs are generated. The electrons move toward the circuit, towards the back contact, and the holes move toward the electrolyte where they can participate in a photoelectrochemical reaction. So again, by modeling the obtained spectra, we draw relations between these discrete parameters, space charge layer resistance and space charge layer capacitance, against measurement potential. So this is potential that had been applied during measurement. And overall, we notice that the space charge layer resistance of the composite is lower, as well as the capacitance of the space charge layer is larger, which would mean that the layer is capacitance is larger, which would mean that the layer is there. And if we examine the steady state photocurrent, which is shown by this dashed line, we notice that with potential it increases. We also saw that in the LSD curves. However, the space charge layer resistance also increases, which is kind of a contradiction. The resistance increases and the current increases. And that is because the photocurrent is proportional to the rate of the occurring photoelectrochemical reaction, whereas this parameter, the resistance of the space charge layer, is instead proportional to the amount of charge carriers that have been generated within the space charge layers, so-called photoconductivity. So it could be called photoconductivity. And we show this by plotting the inverse of the space charge layer resistance and by calculating a sort of rudimentary derivative by dividing the photocurrent by applied potential. And we also obtain a very similar tendency for which a lot of the points even coincide. So with this, we claim that the RC is a measure of photoconductivity. And that means that the photoconductivity of these composites is larger, that means more photoexcited charge carriers are generated within the space charge layer. And finally, very briefly, I will mention that these composites also, because they contain molybdenum sulfide, they can act as hydrogen evolution electrocatalysts. Shown here are two polarization curves, one obtained for a tungsten oxide sample, which reaches about 100 milliamps per square centimeter at 0.6 volts applied over potential, whereas the composite, which is these values, have much lower potential because there is electrocatalytically active molybdenum sulfide on the surface. And again, we apply the same electrochemical impedance spectroscopy analysis by modeling and calculating adsorption resistance values, and we obtain, again, by this point, not unexpected results that the adsorption resistance is much smaller for these samples that contain molybdenum sulfide and are thus electrocatalysts. And finally, these samples, these composites, are because they have possibly uneven dispersion of molybdenum sulfide throughout the tungsten oxide matrix. They're also a very interesting candidate for local hydrogen evolution reaction electrocatalytic activity measurements by scanning electrochemical microscopy. So these samples were also investigated in much the same way as the previous ones, only these ones, we assume that the tungsten oxide does not actually evolve hydrogen under these applied conditions, whereas molybdenum sulfide should. And here a slightly larger probe was used, and this map is 1 millimeter by 1 millimeter, if you'll notice. And we do find some hotspots in this heat map, which the signal here means that hydrogen evolution occurs more rapidly at these spots. But by comparing this to surface morphology, we cannot really relate this to any micro or nanostructures, because as can be seen, this small spot represents this entire piece of surface morphology, and the microstructured nodule surface is even smaller than that. So these large structures could be related to either topography of the sample, if it is very uneven, and here maybe some profilometry measurements could help, because profilometry does show larger topographical information, or there could be some macro distributions of molybdenum sulfide within the film. So this may be a potential avenue for more research. That concludes my data on the characterization of these samples. So overall, molybdenum sulfide is really a versatile material. It can be used as an electrocatalyst by itself due to its properties. It can also be used as a semiconductor of a lower band gap, and it could be used to form heterojunctions with other materials that have larger band gaps, and thus create a more photocatalytically or photoelectrochemically active composite. And especially electrochemical impedance spectroscopy and photoelectrochemical impedance spectroscopy allow us to circumvent the calculations of surface area, geometrically active surface area, or specific surface area, and operating parameters that are more perhaps directly comparable, at least for the samples that had been measured under similar parameters. So thank you. I'd like to acknowledge obviously the funding from the projects, from my projects, and thank you very much for your attention and sitting through my presentation.
Thank you, Ramunas, for a nice presentation, as always, and nice data.